Aloha class. I'm sorry I'm not with you today. I'm out of town, but I have prepared a lecture about Chapter 4 in McMurray on the third edition about cycloalkanes and their stereochemistry. This is a part of the course in which you absolutely have to use molecular models. The lecture will be in several pieces because of the technology, and I urge you to read these, watch these lectures, pause them, and build molecular models at the same time. Cyclic structures are widely seen in organic chemistry. They're also quite present in the natural products. These are molecules that are formed in bacteria, plants, and fungus, many of which have biological properties. You can see the three-membered ring here in red, the five-membered ring, and a six-membered ring. This is the backbone of steroids, everything from the birth control pill to testosterone to estrogen. And you can see it always has these three six-membered rings along with a five-membered ring. The chemical shorthand symbols are the triangle for a three-membered ring, a square for the four-membered ring, a pentagon for the five, and a hexagon for the six. These are not very accurate descriptions of the molecules, but they're shorthands. Here are more accurate descriptions of the molecule. You can see a three-membered ring cyclopropane, a four-membered ring, a 5, and a 6. In the three-membered ring, obviously the three carbons define a plane, and it is a very rigid structure. If you try to make this with your molecular models, you may actually break the models. It's going to be hard to put this together. Remember, a tetrahedral carbon atom wants to be 109.5 degrees, but in cyclopropane, all of these ring bond angles are 60 degrees. Plus, there is an eclipsing interaction between each of these CHs on the top face and the bottom face. The cyclobutane reaction, the cyclobutane molecule, has a bit more flexibility than the three-membered ring. Three of the carbons will be in plane, but as we'll see, a fourth will be out. The five-membered ring has even more flexibility, and then the six, and so on. How do we name these? Well, the simplest way is to think of the ring as the parent structure. In this case, it's substituted with a methyl group. A hydrogen on the five-membered ring is replaced by methyl. And so the name of the molecule is methylcyclopentane. You don't have to give it a number. By convention, there's only all the hydrogens in cyclopentane are equivalent, and so it's understood that this is one methylcyclopentane. You can also consider the ring to be on a substituent. Here is butane. We can think of the three-membered ring as one cyclopropyl butane. If there are two substituents, we always try to use the smallest numbers. So we would number in such a way that it would be 1,3-dimethylcyclohexane rather than 1,5. So we always number in such a way as to have the smallest numbers. Not very different than what we do with the non-cyclic or the so-called acyclic alkanes. If there is confusion, you actually then go to the third and fourth substituent. 1, 2, 4 is a smaller collection of numbers than 1, 2, 6. So you're always numbering in such a way as to have the lowest possible numbers. And then we use the alphabet. Ethyl comes before methyl. We don't alphabetize based on the di in dimethyl. We would call this 1-ethyl-2-methylcyclopentane rather than 2-ethyl, 1-methyl. When you have a choice, we'll call the substituent that has priority due to the alphabet, number 1. So we would call this 1-bromo-2-methyl, and rather than 2-bromo-1-methyl cyclobutane. Again, we follow the alphabet: bromine, ethyl, methyl, and we will call this 1-bromo-3-ethyl-5-methyl rather than other possible combinations. You can call this 2-cyclobutyl butane. I would not mark that incorrect. You could also call it methylpropyl or sec-butyl cyclobutane. All of those known names would be correct. In this example, chlorine followed by ethyl followed by methyl in the alphabet, and we number in such a way that the chlorine comes as number 1 rather than the second or the third substituent. Perhaps the most critical difference between a cyclic and an acyclic molecule is rotation. You remember that your models of ethane, there's free rotation about this bond. You have conformers with different energies, but the energy barriers are small. And for that reason, all of these 3 hydrogens on this method are chemically equivalent and are actually chemically equivalent to the hydrogens in the back. Here is a here is a ball and stick model of ethane in its most favorable standard configuration. We can rotate it to form the slightly higher in energy eclipse conformation, and then of course it will keep rotating. But in cyclopropane, there is no free rotation about any of these bonds, and that has important consequences for isomerism. And so, whereas in propane, substituents on the 1 and 3 carbon may exist, the molecule may exist in different conformations. When you have no free rotation around this bond, you actually now get separate molecules. Here the 2 CH3 groups are on the same side of the molecule. Here they are on different sides of the molecule, different faces of the molecule. In order to convert one to the other, you would have to heat this to a rather high temperature, break a bond, and rotate. You can see the ball and stick model here that the 2 methyl groups are very close to each other in the what is called the cis or the Z form of the molecule, of the Z molecule. And in this form, the methyl groups are pointing away from each other. They're not banging into each other. We call this trans 1,2-dimethyl cyclopropane. This is a separate molecule which can be isolated, distinct from this molecule. They have different chemical and physical properties. Which of the 2 molecules do you think is more stable? Well, you simply think about it in terms of the interactions between these groups. Here these methyl groups bang into each other. Here they don't. The trans form is more stable than the cis form. These are called constitutional isomers because you actually have to break a bond to reconnect them. This is branch, this is linear. These are called stereoisomers because they don't differ in the connectivity of the atoms. They differ in the direction, the stereo, the 3-dimensional orientation of the molecules. This does exist in all cyclic molecules, not just cyclopropane. You can see that in cyclobutane you have a choice between putting the methyl groups on the same side, the top face of the molecule, or you can envision a dimethyl cyclobutane in the trans form, in which this methyl group here and this hydrogen here switch positions. We always put the labels cis and trans before the numbers and the names of the substituent. This is trans 1-bromo 3-ethyl cyclopentane. So think about these for a minute and then think about how you would name them. Is it cis or is it trans? Cis or trans? Well, we first identify the ring, the 5-membered ring and the 6-membered ring, and we see from the heavy line and the dotted line that this is going above the plane of the ring. Imagine this 5-membered ring is in the screen. This is going above the screen. This is going into the screen. Whereas both of these are going into the screen. So this is trans 1,3-dimethyl cyclopentane. This is cis 1,2-dichlorocyclohexane.